Imagine you are building a highly complex machine, one where every single component is interconnected and relies heavily on a few specific parts. If those few critical parts fail or are slightly different in a new environment, the whole machine might collapse. It becomes fragile, right? In deep learning, the dropout rate is absolutely essential because it acts as a powerful regularizer, preventing your neural networks from memorizing training data and ultimately improving their ability to generalize to new, unseen examples. When a neural network trains, neurons can sometimes learn to co-adapt too much, meaning they relying heavily on the presence of specific other neurons. This makes the network brittle and prone to overfitting, where it performs exceptionally well on training data but poorly on anything new. Dropout combats this by randomly deactivating a fraction of neurons during each training step. Think of it like training many different, thinner networks, each with a different subset of active neurons. This forces each remaining neuron to learn more robust features independently, as it cannot relying on its neighbors always being present. It creates a more resilient and less specialized network. The dropout rate specifically determines the probability of a neuron being dropped, directly controlling the intensity of this regularization technique. Practically, choosing the right dropout rate involves a bit of experimentation and understanding your model's behavior. Common rates range from 0.1 to 0.5, which translates to 10% to 50% of neurons being dropped. A higher rate means more regularization, which can be beneficial if your model is severely overfitting, but might also hinder the learning process if set too high. Conversely, a lower rate offers less regularization, which could still lead to overfitting if the network is complex. Dropout is usually applied to the hidden layers of a neural network, but it can also be used on input layers in certain specialized scenarios. This random deactivation during training effectively creates an ensemble of many different neural networks. Instead of training one huge model that might be overly specialized, Dropout trains many slightly different models, all sharing their underlying weights. At inference time, all neurons are active, and their outputs are scaled by the dropout rate, effectively averaging the predictions of these numerous implicit subnetworks. This averaging effect is a key reason for its effectiveness, as ensembles are often more robust and accurate than single models. It is a computationally inexpensive way to achieve powerful ensemble benefits without the overhead of training multiple separate networks from scratch. By judiciously applying dropout with an appropriate rate, you are not just arbitrarily turning off neurons. You are intentionally building a more independent, robust, and generalizable deep learning model, ensuring that the features it learns are truly representative and useful for solving real-world problems beyond the training set.